Hi everyone, this is the second part of Lecture 3 of Astronomy Geoscience 160, Life in the Universe. This section of lecture, we're going to be talking about light and the fingerprint of the elements. We all are familiar with what light is. Light is what lets us see. Without light, we are literally kept in the dark. Light also keeps us warm. Light from the sun is what warms our planet and keeps us at a comfortable temperature and keeps us from being too cold. But I want to talk now about what physicists mean when they think about light. When a physicist thinks of light, they think of it as a form of energy that travels as a wave. This kind of makes sense, right? That light might carry energy because we know that light from our sun is what keeps us warm. So that's energy from the sun keeping us warm. But the sun is very far away and it's not touching us. So somehow that energy has to get from the sun to us here. And that is through light. In particular, it turns out that light is a wave in what we call the electromagnetic medium. So light is an electromagnetic wave. Electromagnetism has two components that we're all probably pretty familiar with as well, electricity and magnetism. So electricity, of course, is what powers our devices. It's what's running the computer that I'm recording this lecture on. On the left-hand panel here, I'm showing an image of a woman who's touching something called a Van der Graaf generator. This generator creates static electricity, and the static electricity builds up a charge, which is then transmitted to her when she touches it and causes her hair to stand up. So the electricity, the static electricity, is causing a force to be applied to her hair to bring it up away from her body, even though gravity would normally pull it down. So electricity can cause forces. And likewise, magnetism causes forces as well. Here's a bar magnet that's being used to stick to some paper clips. If I were to lift this magnet up, those paper clips would go with it. So that bar magnet is applying a force to those paper clips to pull it upwards. And it force is strong enough that it'll resist gravity from the Earth. So the magnetic force can apply forces that are equal to or greater than the force of gravity here on Earth. When physicists think about forces, they usually try to think about them and visualize them in what we call fields. So there are electric and magnetic fields that we use to visualize how things behave in the presence of electricity and magnetism. So this is a little bit of a weird concept, but I'm going to try to explain it with these images here. So starting over here on the left, this is an image of two plates of metal. So this is one plate and this is another plate. And these two plates have been charged by some sort of electric force, so that this plate now has a positive charge and this plate now has a negative charge. Now, in previous lectures, I told you that positive and negative charges will attract each other and like charges will repel each other. But in this case, these plates are fixed in place and they're not going anywhere. Instead, what I want to think about when I visualize electric forces is what happens to a third particle. Suppose I have some other particle with a force and I put it anywhere in this image. Where will that particle go? And the answer is, depending on what its charge is, it will travel along these lines. It will be pushed in the direction of these lines that are being created in this diagram. So the idea behind electric force fields is the field tells us where the force will be applied at any location on this diagram. If the particle is put out here, then the force will be applied in a direction like this. But if the particle is put right between these two plates, it'll go basically straight to the other plate. The same thing is happening here on the right-hand animation with a magnet. So what's happening here is there's a magnet that's being dropped onto a trampoline, and it's being dropped onto the trampoline in the middle of a bunch of iron filings, which are small pieces of magnetic material. So when these filings are bounced into the air, you can see themselves arranging into these curved lines. These lines trace the force that the magnet is applying to them. And you can see that these lines extend far out here. These electric and magnetic fields are really a way for physicists to understand how forces will apply to objects and how objects will behave when they're in the presence of electric and magnetic phenomena. So the other thing that I want to make clear here is that even though electricity and magnetism may seem totally different, you've never, for example, had to plug something into your magnet to get it to stick on the refrigerator. It doesn't require, electricity from the wall to do that. These two phenomena are really intimately connected. So what I'm showing here are two GIFs that show how magnets, so this is a magnet here, and electricity can be used together to create forces. So in this case, if you have a wire that touches the top of this battery, so you have now electric current flowing through the wire, it touches the bottom of this magnet, and it's in the presence of this magnetic field and there's a current flowing, it will cause this wire to rotate, to spin. This is a simple motor, essentially. And you can do this over here as well. If you have two wires or two magnets and you connect them with a wire, you can make a little car almost that rotates this battery. This is another simple motor. So electricity and magnetism, when combined together, can apply forces in different ways than they could otherwise. And in particular, they can cause rotational forces. So the idea here is that curling electric fields create magnetic fields and vice versa. So what I'm showing here is something called an electromagnet. So there's wire here that's wrapped around this core, and the wire is wrapped in this coil. So we've now curled electricity on and around itself. This creates a magnetic field. So now when we turn on this magnet, when we send current through this coil, it behaves the way a magnet would and can lift up paper clips the same way we saw that magnet do earlier on. In the same way, a curling magnetic field can cause an electric field. And when you put these two things together, they can actually interact in such a way that you can create a wave in which you have a changing electric field that curls around a magnetic field, which essentially propagates forward the electric field and the magnetic field together, essentially forever. This is light. Light is the interaction of these two fields reinforcing and recreating each other forever and ever until they hit something. They can go through vast distances of space doing exactly this until, for example, they hit our telescopes. So without all that being said, I now want to take a quick break and go into properties of waves. So we just said that light is an electromagnetic wave. So to understand the properties of light, it's helpful to understand what some of the properties of waves are in general. So the first property of a wave that we can measure is something called its speed. So speed is something that's familiar to us all, how quickly something moves. In particular, for a wave, we want to measure how quickly a certain point on this wave moves. So how quickly this trough moves or this peak moves. So what we can do is we can measure the peak. We can see how long it takes this peak to travel a certain distance. And then we can divide the distance that peak traveled by how long it took to get there. And that gives us the speed of the wave. Typical speeds of waves vary greatly depending on what they're waves in. So for example, the typical speed of a wave in water in the ocean is about 5 to 20 miles per hour. But the speed of light, the speed of these electromagnetic waves are much, much faster, about 670 million miles per hour. Another property of a wave is called wavelength. And this is pretty straightforward to measure. It's just the distance between two consecutive peaks or troughs in the wave. So we can just take a ruler, for example, and measure that for this wave in water here. The third property of a wave that we were going to talk about is its frequency. This is a little bit more tricky to measure. And the way you measure the frequency of a wave is you see how often a peak or a trough travels through a certain point. So what I've done here is I've marked a certain point in this wave with this pink line. And what I want to do is I want to start a timer at the time when a peak of this wave hits this pink line. And then we want to measure a certain amount of time and see how many peaks or troughs go through that point over that time. So what I'm going to do in a second is I'm going to start this timer here when a peak hits, and then I'm going to let it go for 10 seconds. And once it gets to 10 seconds, I'm going to stop it. And over that time, we can figure out how many times that peak has gone, how many peaks have gone through that point. So I'm going to start it on this next peak right here, go. So if you count, you can watch this clock go upwards and see how many peaks and troughs go through this point here. And now I'm going to pause here. And I counted that there were 4 times that the peak went through that line over those 10 seconds. So the frequency is the number of peaks that pass through that time, which is 4 in a given amount of time. So the frequency is 4 cycles per 10 seconds. Or if you just do that division, 0.4 cycles per second. So these 3 properties of a wave are related by this equation here. The frequency is equal to the speed divided by the wavelength. In general, speeds of waves are relatively fixed. The speed of light is always the speed of light. So what that means is that when speed is constant, if this equation is to hold true, if you change the wavelength, you have to change the frequency in the opposite direction. So a wave with higher frequency in general has a smaller wavelength, and a wave with larger wavelength has a smaller frequency. So frequency and wavelength go against each other in general for waves. The final property about waves that I want to talk about is how much energy they carry. And this depends a lot on what the wave is in. You can imagine that the amount of energy carried by a wave in water is going to be a lot less than the amount of energy carried by a wave in air, for example. Because if you've ever been in the ocean and you've felt what happens when a wave hits you, it can knock you over. But waves in the air, such as sound waves, very rarely have enough energy to knock you over. In general, though, a rule is that the higher the frequency of the wave, or the shorter the wavelength, the more energy is carried. So the faster that those peaks and troughs go through a certain point, the more energy that there is. All right, let's go back to light now and explain how some of these concepts relate specifically to the case of light. We perceive different wavelengths of light as different colors. So what we're showing here is light that's being passed through a prism. And this prism is affecting different colors of light, different wavelengths of light slightly differently. And what it does is it causes the light to spread out. So after it goes through the prism, you can see that the light has spread out into its different colors. The blues and the purples are over here, and the reds are over here. One question that you might ask is, why does light stop here and here? Is there such a thing as light that is redder than the reddest light that we can see, such as light that would be bent over in this direction? Or is there such a thing as light that is bluer than what we see over here? And it turns out that the answer is yes. The light that we can see is actually only a very tiny fraction of all of the light that exists and all of the possible wavelengths. So here's a schematic showing the different types of light, the different wavelengths of light. Over here, we have very short wavelengths. Now remember, short wavelengths means high frequencies, which means high energy. So over here, we have very short wavelength, high energy light, such as gamma rays and X-rays. Then in the middle, we have light that we can see with our eyes. We call this visible light. And then towards longer wavelengths or lower frequencies or lower energy, we have infrared light, microwave light, and radio light. Radio waves are actually light just like the light that we can see with our eyes, but they have much longer wavelength, much lower frequency, and therefore much lower energy. It turns out that certain types of light, in particular light with short wavelengths and high frequencies, and therefore high energy, can be harmful to us. So over here, you can see that X-rays and ultraviolet light have higher energy than the light that we can see with our eyes. And that's why we have to worry about too much exposure to these types of light. For example, when we get too much ultraviolet exposure, we might get a sunburn, so we wear sunscreen. And if you're an X ray technician, you might want to wear protective clothing to keep you from being bombarded by high energy X rays all day, every day. Because if you get too many of those X-rays, then the energy in those light beams and those light rays, light waves can harm you and harm your body and eventually cause cancer. All right. So now I want you to recall back to our quantum mechanics lecture, where we learned that particles that are trapped have discrete possible energy levels, just like waves that are trapped between a person's hand and a farm fixed position over to the other side have certain discrete possible levels in which they can vibrate in stationary ways. The hydrogen atom is perhaps the most common trap in our universe for a particle. So the reason it's trapped is because the proton and the electron have opposite charges and therefore attract each other. Remember from a previous lecture where we talked about how opposite electric charges attract. So, for example, this poor cat has now become oppositely charged with these packing peanuts, and these packing peanuts are now stuck to that cat. The electron is trapped by the proton because the proton is much more massive and much bulkier. So it essentially keeps the electron near to it, and their mutual charge attracts them together. Therefore, the electron has discrete possible energy levels because it is trapped. This is what they look like. These are the locations, the wave functions of electrons in different energy levels and with different possible configurations within energy levels. You can see that some of the lower energy levels, the ones that have the lowest amount of energy, have the electron very close to the proton. But as you have higher and higher amounts of energy, the electron can move further and further away, essentially being able to climb higher and higher away from the proton before having to fall back down. So these different configurations have different energies, and there's nothing in between each of these levels. You can't jump from n equals 4 to n equals 3.5. There is no such thing. So if you happen to have an electron in the n equals 3 energy level, the third energy level, what it will do is it will either hang around there, occasionally it will jump to another energy level. Imagine that that electron jumps down to one of the other possible energy levels. It jumps from the energy level number 3 to the energy level number 2. When that happens, that energy has to go somewhere, and it goes into creating light. So the electron falling to the lower energy level releases a burst of light. So it causes this oscillation in the electric and magnetic fields, which then travels forever as light. But instead of looking like this, it looks like just a quick burst of light where you have the electric and magnetic fields essentially got to have like a packet, like a little bell-shaped packet that allows it to travel on forever. So we call this little packet, this little individual particle of light, essentially a photon. The amount of energy lost by the electron is always the same when it goes from n equals 3 to n equals 2, because those energy levels are determined by quantum mechanics, by physics. So what that means is that every single time a hydrogen atom loses an electron, has an electron that loses an energy level, it goes from n equals 3 to n equals 2, it releases exactly the same amount of energy. That light has exactly the same frequency, therefore, because the frequency of light is related to the energy. And the frequency of that light means if it has exactly the same frequency, then it has exactly the same wavelength, and therefore exactly the same color. So electrons in hydrogen atoms can only create light with specific energies, and therefore hydrogen can only produce light with a handful of specific colors. So what does this mean in practice? So what I want to do now is I want to show you an image of hydrogen gas inside of a light bulb, essentially. So what we're doing is we're passing electricity through hydrogen gas. And what that does is it raises the electrons up to higher energies. The electricity brings energy to those electrons and brings the hydrogen up to a higher energy level. Once it does that, those electrons then fall back down to lower energy levels and release that energy as light. So if we then spread out that light into different colors, exactly the same way we did, for example, with that prism, what we will see is instead of seeing a rainbow, we will see only a handful of different sharp lines in the light from hydrogen. So you can see a red line, you can see kind of a blue line, and then you can see a couple of purple lines. This is called the spectrum of hydrogen, how much light there is at every different color. And the positions of these lines, the positions of these sharp uh, features when you get these energy level transitions from hydrogen is hydrogen's spectral fingerprint. This is unique for all different atoms. No atom has exactly the same lines that are produced. And because of that, we can look at different elements and we can figure out what they are based on what lines they produce. Here are a couple of elements that have different line patterns. So here's hydrogen, the same one we just saw. Here's what neon looks like. There are lots of red lines and they're very dense. And here's a mercury emission spectrum where you have some green lines and some purple lines. We can measure these fingerprints in the lab, or we can calculate them from the Schrodinger equation in simple cases. And if we measure the positions of these lines, these fingerprints, we can then look at light from some other source where we don't know what it's made of and figure out what elements make it up. One of the ways that we show this is in what we call a spectrum. This is just a graph of how much light there is at every different color or at every different wavelengths. So throughout the course, we will show you plots that look like this, graphs that look like this, where on the y-axis, you have the brightness of some object, and on the x-axis, you have the color of light or the wavelength of that light. This is the plot for hydrogen, where you can see that there's a sharp feature, a sharp emission line at about 650 nanometers. There's a sharp one at about 480 nanometers. This is in the teal. And then there are some other smaller ones in the purple and in the violet. So for some historical perspective about this, I'm going to show you another clip from the NOVA series, Fabric of the Cosmos.
So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun. How a ball arcs through the sky. How ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Okay, now that we finished that, I wanted to end with one last caveat. In this lecture, I've showed you spectra of objects that have sharp lines, but not all objects produce spectra that look like that. In some cases, especially from dense objects that produce their own light, the lines that you see are smeared out quite a bit, and often are smeared out so much that you can hardly tell that there are any lines at all. Instead, what you end up with is a spectrum, the amount of light at different colors, that looks something like this. We call this a black body radiation curve. So the light is smeared out in this characteristic skewed bell shape. And there are a couple of things to notice about this. Number one is that there are no lines that are superimposed on top. In a perfect black body, where everything is totally smeared out, you get this very smooth curve. The other thing to notice is that the hotter the object is, the bluer the light is overall. That kind of makes sense, right? The hotter something is, the more energy it has, therefore the higher energy light it will release. And we know that blue light and stuff in the ultraviolet and X-rays and gamma rays are higher energy than visible light and red light and infrared light.